Okay, let's try some practice calculation problems. These sometimes you already have these. We can try them out. And the first problem says, okay, what is the molar solubility of AgCl in pure water at 25 degrees Celsius? The temperature's here specifically because you know that the KSP is temperature dependent. So in that sense, it's given, but that's the only reason why the temperature generally is required. Alright, so what is the molar solubility of AgCl? The first thing I do is I start writing out my equation. AgCl goes to Ag plus Cl minus. I know this thing is balanced, 1, 1, 1. So when I write out my KSP expression, it will equal the concentration of the Ag plus times concentration of the Cl minus. Okay? And it wants to know what's the molar solubility at this would be, because this is the maximum solubility, which would represent at equilibrium. So initial Stoichiometric ratio, equilibrium, solids do not play a role, and they're saying pure water. So I have nothing in there beforehand. So, and they want to know the concentration of basically these items. Well, technically they want just the silver chloride, but all these numbers should be the same. Now, as this thing starts to dissolve, I will gain X of this guy, and I will gain equal amount of X of that guy. Complete these two items together, and you get X and X. Again, right now we have zeros in there, but eventually we'll upgrade this to have something other than 0 in there. So my KSP, which is given right here at 1.8 e to the negative 10th, equals x times x, or x squared, square root 1.8 e to the negative 10th, and we get the x concentration. Alright, we got at this point from my calculator x equals 1.3 e to the negative 5th. Now again, this is the x value. It represents the concentration of the silver ion. It represents the concentration of the chloride ion. And also, because every AgCl, there's one silver, one chloride for every one silver chloride, this is also my answer for the molar solubility of AgCl. They're all 1:1:1 ratios. Okay. Again, you can pause this video to see a little bit more, try it yourself, and then stop back and see if you get the right answer. Here's another similar problem. Alright, so we got lead iodide is dissolving. So first thing I do, PbI2 comes from, again, I draw the reverse arrow, but I don't know that anyone would mark it wrong if you just put a regular yield sign. Pb2 plus I minus 1, and there's 2 of them. Now right off the bat, I note this 2 here. To me, that means something. It means it's going to add one more step with my equilibrium expression. My KSP, which is 7.9. Well, if they ask you to write the equilibrium expression, if they ask you to write the equilibrium expression, then you can just leave it as K there. You don't have to put the value in. So they just ask you for the actual KSP expression. You just got to go KSP equals, and it would be 7.9. Well, hold on a second. So put the values in here. Again, you don't need to necessarily include that. Just go KSP equals the concentration of the lead ions, Pb2 plus, concentration of the iodide ions, and this one gets squared. So if they say just give me the equilibrium expression, that's it. Now, what do they want us to do for this problem? They want us to determine the molar solubility of the lead iodide. Not the lead ions, not the iodide ions, they want the lead iodide. So again, I have my formula. I'm going to put it right here, right there, but I'm going to let's redo it right here. Something here. Okay, I got PBI2 goes to PB plus 2 plus 2I negatives. Initial stoichiometric ratio end. Solid not playing a role. Nothing in there before I start. Going to gain x here. Going to gain 2x here. X and 2x. And after you do this a bunch of times, you realize it's always the same. Plug my x values into their correct spots and solve for x. This is going to be 7.9 e to the negative 9th equals, in this case, x times 2x squared, which always comes out to 4x cubed. And you would simply solve for x. Divide by 4, raise the whole thing to a quarter, 1/3 power, and x equals the concentration of, in this case, the lead ions. 2 times that would equal the concentration of iodide ions, but because it's a 1-to-1 ratio of the lead, this would equal the concentration of the lead iodide as well. And the actual answer to this thing is, in case you're questioning your math, you can try it out. 7.9 exponent to the negative 9th divided by 4 raised to the power of 1/3 equals. In this case, it is 0.00125, and that would be a mole per liter, and that is the answer to the question that they are asking. We've done 2 problems, very similar, only that one has a 2 in the coefficient, which causes a small issue. Other than that, we will run through some more problems in the next video.